Presento a la doctora Anna May Diehl, que es una experta mundial en el tema. Ella es profesora de medicina de Duke University y hablará sobre fisiopatología de esteatosis hepática no alcohólica.
Thank you very much for inviting me. I have not been to Mexico City for a number of years, and it's even bigger and more beautiful than I remember. I'm supposed to talk to you about the pathophysiology of NAFL and NASH, and we're going to focus on some of the things that you've heard from earlier speakers today, namely obesity, immunology, and the gut-liver axis. Obesity is a big problem for us in the United States. 1/3 of American adults are obese. And we know that obesity is associated with liver disease, NAFLD or non-alcoholic fatty liver disease. At least 1/4 of the United States population has some form of fatty liver. Probably 1/4 of the people with fatty liver have NASH, non-alcoholic steatohepatitis, the more serious form of fatty liver disease. And although we don't know for sure, we think that about 25% of people with NASH will go on to develop advanced fibrosis and cirrhosis. Once cirrhosis develops, the risk of hepatocellular carcinoma is at least 1% per year. In the United States, fatty liver disease has become our major type of liver disease, and the incidence is rising because of the epidemic of obesity in our children. So we need to try to figure out why obesity causes liver disease. And today I'm going to tell you a little bit about what has been learned about the metabolic syndrome, because we think that is how obesity causes damage, not just to the liver, but probably to all tissues in the body. This morning, I think many of you heard the beautiful lecture by Dr. Souza on Barrett's esophagus, and I want you to keep that in mind as I talk about the metabolic syndrome, because many of the factors that she talked about are involved in the metabolic syndrome. During this lecture, I'm actually not going to talk too much more about the liver, but I'm going to focus on other tissues that are involved in the metabolic syndrome, because liver disease in the metabolic syndrome is related to disease outside of the liver. So what is the metabolic syndrome? It's a constellation of metabolic abnormalities that are associated with visceral adiposity, and those include insulin resistance, hypertension, lipid abnormalities. It's confusing to figure out what that means, and so I went to Wikipedia. And Wikipedia defines the metabolic syndrome as a disorder of energy utilization and storage. So this defect in energy homeostasis causes damage in various tissues. The number 1 cause of death in the metabolic syndrome is heart disease. The number 2 cause of death is cancer. And the number 3 cause of death is liver disease. It's also associated with type 2 diabetes. The prevalence of the metabolic syndrome is very high in almost all parts of the world. About 25 to 30% of many different populations have the metabolic syndrome. And if you remember back to the slide I showed you a few minutes ago, that's about the prevalence of fatty liver disease in the United States. The metabolic syndrome is thought to be a chronic inflammatory state. And there are 3 major organs that are the key sites of inflammation initiation in the metabolic syndrome: the liver, the fat tissue, and the gut. And in all of these tissues, it's thought that there are common initiating signals that induce some sort of chronic metabolic state that eventually leads different kinds of cells in those tissues to commit suicide or to undergo apoptosis. And what we'd like to do for the remainder of the talk is review the mechanisms that initiate inflammation in the metabolic syndrome. And that is going to be important to us as doctors, because if we understand how inflammation promotes organ dysfunction and damage, we might have better ways to diagnose and treat people with the metabolic syndrome, including people with NAFLD. So in general, what we've learned is that metabolic stress occurs in key cells that coordinate energy balance, such as fat cells or adipocytes, hepatocytes, and pancreatic beta cells. These stressed cells emit signals that activate our innate immune system, and then that leads to chronic inflammation. So what is the innate immune system? Well, it's our first response to primal survival threats. We are hardwired to generate effective immune responses, and this hardwiring is called the innate immune system. And we have it so that we can survive in the real world. It protects us from foreign invaders. Those invaders could come from outside of our body, like pathogens, or they could come from inside of our body, like malignant cells. This is a very powerful system, and as the cartoon suggests, it can turn out to have some adverse consequences. So it's kept under very tight control. And you actually have to have two signals to activate the innate immune system. Something associated with your body being invaded by a foreign cell or cancer. These are often called pathogen-associated molecular signals, or PAMs. And an example of one of a PAM would be lipopolysaccharide endotoxin LPS. But it's not enough just to be exposed to risky things. You actually have to demonstrate that those risky things are killing cells in order to activate the innate immune system. And the damage signals from the wounded cells are called damage-associated molecular signals, or alarmins. And these are things that the damaged cells release. And an example would be ATP. And so when you have a combination of these invader-associated signals and the damage signals from the wounded cells, the innate immune system turns on. It produces inflammatory cytokines. And it's these cytokines that are the effectors of the innate immunity. They are good because they kill invading pathogens and tumor cells, but they can be dangerous. Early this morning at Dr. Souza's talk, she mentioned briefly the inflammasome. If you try to read the literature about the metabolic syndrome and a lot of the diseases that are associated with it, you keep running into that word. What is the inflammasome? Well, inflammasomes refers to complexes that occur in various kinds of cells, and they have an abbreviation. One is called NLRP3, the other is called NLRP6. So let me walk you through what it means to activate the inflammasome. So you'll see on this slide signal 1. Signal 1 would be a signal from a pathogen like LPS. It binds to a receptor on the surface of cells and leads to the activation of intracellular signals that cause transcription factors like NF-kappa B to be activated. And those transcription factors drive the synthesis of pro-inflammatory cytokines. But those pro-inflammatory cytokines are so dangerous, they're not just made in an active form, they're actually made in an inactive form. In order to activate the inactive pro-inflammatory cytokines, you need the second signal. The second signal comes from damaged host cells. An example might be crystals from gout or ATP from a cell that dies. They bind to their receptors, and it's that signal 2 receptor signaling that leads to the activation of these molecular complexes that they call inflammasomes. The inflammasomes activate an enzyme, caspase 1, and the caspase cleaves the pro-cytokine and makes it an active cytokine. So if you activate signal 1, you get the precursor cytokine. If you activate signal 2, the precursor cytokine becomes activated, and now you have pro-inflammatory cytokines being released. This can trigger a cascade because almost all cells in the body have receptors for these pro-inflammatory cytokines, and if you read through that complicated bunch of stuff, what you'll see is that these pro-inflammatory cytokines will activate their own synthesis. So once you start the inflammatory cascade, it tends to perpetuate itself. So obesity promotes inflammasome activation. And we'll talk a little bit about how it does that, but it increases cell death, so it provides signal 2. It increases the production of cytokines, so it helps to provide signal 1. And it also increases bioavailability of gut-derived bacterial products like LPS, another way to increase signal 1. So I'm not going to talk today about cell death. We'll talk more about that tomorrow. But today I'm going to talk about the pro-inflammatory cytokines and the gut-liver axis. So as I said before, there are 2 or 3 major tissues that are involved in making the inflammatory cytokines that occur in the metabolic syndrome. One is the fat, and one is the liver. So the fat from people that are obese has evidence of inflammation. It's making these pro-inflammatory cytokines, and that makes the tissue insulin resistant. When the tissue is resistant to insulin, it can't absorb fatty acids, and so the fatty acids circulate around, they go to the liver, and they can create toxicity in the liver, and then that activates the inflammasome in the liver, leading to these cytokines, and you get this vicious circle. So how does being obese cause you to have inflammation in your fat? Well, it turns out if you're not fat, you actually have anti-inflammatory mechanisms in your fat tissue. And these are cells, macrophages, and other kinds of cells that are making chemicals that are squelching inflammation. But when you become obese and you're calorically overloaded, you actually activate an ancestral caspase that protects you from starvation. And it's a mistake. And my lab has recently published evidence about this. It's actually kind of ironic. In the days long, long ago when our ancestors didn't get enough to eat, they wanted to have a mechanism if they were starving to kill unnecessary cells. So fatty acids accumulating in cells was a sign of starvation. It activated a caspase that killed the cells, and that was a good thing. But now fatty acids accumulate in our cells not because we're starved, but because we're overfed. But we activate that same ancestral caspase, and so the cell reacts as if it's starving, but it's actually obese. And so there's an increase in cell death that activates the inflammasome. The inflammasome recruits in these inflammatory cells that make inflammatory cytokines. This process feeds on itself, as we talked about earlier, because once you get the inflammatory cytokines, you tend to get more inflammatory cytokines, and eventually you get an adipose tissue that has a lot of inflammatory cells in it, a lot of cell death. And in order to try to protect themselves from the thing that triggered this, remember it's the fatty acids that triggered it, the fat cells start to make chemicals to protect themselves from taking up fatty acids. One of the chemicals that makes the cells take up fatty acids is insulin. So all these chemicals that the fat cells make, resistin, leptin, all of those things, TNF, prevent insulin from being effective. So the fat cell becomes insulin resistant to defend itself from fatty acids so that it won't activate that killer caspase. But as a result, it becomes insulin resistant. And then these things are floating around in the blood and attacking other tissues. And so that's why when we see patients, the process has already started and it's difficult to tell the chicken from the egg. Is it the fat that got the process started, or did the liver get it started? People debate that. In reality, it probably doesn't make any difference because it's a self-reinforcing cascade. So I told you in the last couple of minutes about why obesity, because of its effects on the fat, increases cytokines, increases cell death, and that will then lead to the inflammasome activation causing more inflammatory cytokines, more inflammasome activation, more cell death. In the next little bit, we'll talk about where the LPS might come from and the effects of obesity on the gut-liver axis. This has become a very hot topic, and it actually began back in 2004 by this seminal paper from Dr. Jeff Gordon's group. He made a very, very interesting observation. He noticed that mice that were raised in a germ-free facility, so they did not have any bacteria in their intestines, were skinnier than conventional mice that had normal intestinal bacteria, even though the germ-free mice ate more. So they were eating more, but they weighed less. He then colonized the lean, germ-free mice with the intestinal flora from the conventional mice, and the germ-free mice began to gain weight even though they ate less. He then went on to figure out how that worked, and he showed that our gut flora actually help us to assimilate nutrients from our diet. They increase intestinal absorption of monosaccharides, and when you have more energy coming into your body, that's a stimulus to make fat in the liver. At the same time, these gut flora also decrease the production of a factor called fasting-induced adipocyte factor that inhibits the uptake of triglyceride that's made by the liver and secreted to be taken up by the fat. So when FIAIF goes down, the fat cells can incorporate more fat and you become fatter. So our bacteria live in us for a reason. They want us to be fat and happy, and so they actually help us to assimilate nutrients from our diet and to store fat. But now there's more to it. He then went on to show that the microbiome in the gut of obese mice is different than the microbiome of lean mice. More importantly, he could take the microbiome from the intestine of the obese mice, give it to the lean mice, and the lean mice became obese. So in a sense, obesity is an infectious disease. He then showed how this worked. He showed that the obese microbiome is enriched with kinds of bacteria that generate certain molecules. One would be short-chain fatty acids that combine to specific receptors on intestinal epithelial cells, make them release certain hormones that change gut motility. And so I know many of you take care of obese patients, and many of those patients have irritable bowel syndrome because they have altered gut motility. That's a consequence of their altered gut microbiome. And so many of my obese patients tell me that they only eat salads, but they gain weight, and they may in fact be right. They are colonized with bacteria that can take things that are normally not digestible and generate fatty acid derivatives that have effects on gut motility and will have the food stay in their intestine longer so that more of it can be absorbed. In addition to changing the absorption of food, though, it's also thought that some of these bacterial products can change the barrier function of the gut and allow more LPS to be assimilated into the body. And remember, LPS can provide one of the signals for the inflammasome activation. So it would seem like what we ought to be trying to do is to decrease the gut bacteria, decrease inflammation, decrease inflammasome activation. But life is complicated. And that was shown by this paper that received a lot of attention in the United States. It was actually cited in the Wall Street Journal and in the New York Times. And this is an example where taking away the inflammasome actually was bad, not good. And let me walk you through this paper. What these authors showed is that the normal gut interacts with the bacteria, and those bacteria activate the NLRP6 inflammasome. That inflammasome makes IL-18, and the IL-18 recruits certain kinds of immune cells into the gut mucosa to keep the mucosal barrier function good and to keep everything quiet and happy. When they deleted the NLRP6 inflammasome using genetic approaches, it turned out that there was no longer any IL-18 made, and the good kinds of immune cells weren't recruited to the gut. Rather, a factor that recruits neutrophils was induced, and neutrophils came into the gut. And somehow, still not well understood, these neutrophil-derived factors then changed the intestinal microbiome to a more dangerous kind of microflora. And as shown on the right, what you can see is when they took wild-type mice and they co-housed them with the mice that had this more inflammatory microflora, the wild-type mice became sick, just like the NLRP6 knockout mice. So again, showing that the bacteria were transferring the genetic trait, and they were transferring it because they were somehow interacting with the host. So I think what we can learn from this paper is that loss of pro-inflammatory cytokines isn't always good. It can, in fact, sometimes be bad because these inflammatory cytokines are somehow interacting with our host microflora. To summarize it up and kind of put it in terms I think that are more helpful to understand, in health we have a balance between pro-inflammatory stress and anti-inflammatory stress. And in the intestine and in the gut, those things have to be balanced. Remember, we talked about in the fat that there's normally a little bit of inflammation and a little bit of anti-inflammation, and the fat is healthy. When you get more pro-inflammatory signals, you overwhelm the anti-inflammatory signals and you get abnormal adipose tissue. And the metabolic syndrome is actually when anti-inflammatory defenses become overwhelmed. If you have a chronic pro-inflammatory state and you want to survive, you have to adapt. And so chronic inflammation results from both loss of anti-inflammatory defenses and gain of the pro-inflammatory signals. So we thought that knowing that, we have to just restore the balance. And one of the things that gets depleted in obese fat tissue are these cells that make interferon gamma that quiet down the immune system. And an example of that are things called NKT cells. NKT cells are depleted in obese humans who have fatty liver. So investigators in Israel thought that if you gave back NKT cells, everything would get better. It sounds like a really good idea, and in fact, it did somewhat help the insulin resistance. However, what we learned is that too much of a good thing is also a bad thing. And then if you give too many NKT cells, what you actually get is a triggering of these anti-inflammatory responses, many of which promote fibrosis. And so in people who have cirrhosis, they actually have an increase in NKT cells in their liver. So the take-home message is we have to get it right. Too little is bad, too much is bad. And you can have progressive tissue damage if you have an overabundance of pro-inflammatory or an excessive amount of anti-inflammatory responses. So in summary, the metabolic syndrome is a constellation of disorders that reflect deregulated energy utilization and storage. It's characterized by chronic immune activation. The inflammation is caused by factors generated by metabolically stressed cells in the fat, the intestine, and the liver. The inflammation provokes compensatory anti-inflammatory mechanisms to dampen the inflammation and repair the damage. But progressive tissue dysfunction can result from either under or over activation of the anti-inflammatory responses. And this cartoon summarizes it in a picture. We have these signals that are activating our immune system, and in the hopes of protecting us, because it looks like we're having cell death. That leads to inflammation. That's a good thing, particularly if it triggers appropriate anti-inflammatory responses to control the response. However, if those anti-inflammatory responses are inadequate, you get tissue damage. But if they're excessive, you also get tissue damage. You can get scarring. So I'll stop here. Thank you.
Le agradecemos a la doctora Mae esta excelente revisión acerca de